Good afternoon, everybody. This is lecture 5, need analysis. So we are continuing our discussion on systems engineering, specifically on the definition of the problem and also the beginning of the development of our systems. So in this lecture, we are going to continue that discussion. And I'm going to teach you some new tools to help in that process of understanding what needs to be done, specifically for a new development. So the material for this lecture is coming mostly from chapter 5 of your book. And this is the agenda for today. So we're going to start with discussing the originating a new system topic. And then we're going to talk about operations analysis, functional analysis, the feasibility definition of a system, the needs validation, and finally, the system operational requirements. So in terms of the primary objectives of the needs analysis of the life cycle, we try to show clearly and convincingly that a valid operational need or potential market exists for a new system or a major upgrade to an existing system. So again, there's a need and there's a market for this need. And we are trying to solve that need by developing something new or by exploring, updating the current status of the existing system. And there is a feasible approach to accomplish this, to fulfill the need, which we are going to try to make it at an affordable cost or within a budget, and in which we are obviously taking some risk, but that risk is something that we can tolerate or is acceptable because we know that is a high chance for us to be able to control. This is achieved in part by devising at least one concept that can show to be functional, capable of fulfilling that perceived need. So we know there's a problem, and I know that at least in paper, I can develop something that is feasible. And then we can describe in sufficient detail to persuade decision makers that this is technically feasible and that can be produced at an acceptable cost. So you can see here in figure 5.1, the needs analysis phase. And you can see that it goes before the concept exploration. So its inputs are seen to be the operational deficiencies or technological opportunities. So there's a need, there's something that we can do about it. And the output to the following phase, which is the concept exploration. And we had two outputs. The outputs for the system operational effectiveness, which basically state what the new system has to accomplish. And the system capabilities, which is the output of various operational analysis and system studies that provides evidence that an affordable system capable of meeting these target is feasible. So in terms of examples in the car industry, government laws require manufacturers to make substantial improvement in fuel economy, safety, and pollution control. So we see every year that there's new ways of accomplishing those goals. For example, in terms of pollution, we've seen the transition to electric cars. In terms of safety, with the use of cameras and automated functions like stopping with sensors. And fuel economy, again, try to get the best performance out of our engines. In terms of technology-driven new systems, applications of space technology to meet important public and military needs. Things like powerful propulsion systems, lightweight materials, and compact electronics all made the engineering of reliable and affordable spacecraft a practical reality. And we have seen how things are being changing. I mean, new technology, such as we don't have to, I mean, we can recycle now our rockets. Typically, you would have a rocket going and then never going back, but now there's a company, I don't remember the name now, that can make those rockets come back, and then you can reuse them, which are very expensive. Another thing that can impact the origination of a system is external events. So, for example, in the defense area, this may be an intelligence findings of new potential enemy threat, a local conflict that exposes the deficiency in the system. And in the civil products area, a triggering event might be a sudden shift in customer demand or a major technological change, such as the discovery of a radically new product, or an opportunity to automate a labor-intensive process. So we have many examples like cell phones, iPads, TVs, the iRobot that cleans your floor, and so on. So the drastic increase in the price of petroleum has triggered an intensive and successful effort to develop more fuel-efficient commercial aircraft, the wide-bodied jets, for example. So we discussed the materialization process of the system life cycle. And in terms of design, the phases of the system development process can be considered steps in which the system gradually materializes. And in this initial phase of the system life cycle, this process of materialization has only just started. So we can see here in the picture, in terms of the need analysis, we only have to define the system capabilities and effectiveness, and we are doing that at the level of the system. So it's the top level. We are not going into the other levels of the hierarchy at this point. So let me just highlight this right here. That's where we are. So how do we apply the systems engineering methods in these needs and requirement analysis? So remember, the systems engineering method has four steps. The needs analysis phase is different from most of the succeeding phases because we don't have a preceding phase. The input comes from different sources, especially depending on whether the development is needs-driven or technology-driven, and whether the auspices are the government or a commercial company. So we can discuss the needs analysis phase in terms of 4 basic steps of the systems engineering method with some adaptations. So starting with the operational analysis or requirement analysis, we can analyze the projected needs for a new system in terms of serious deficiencies of current systems or the potential of greatly superior performance or lower cost by the application of technology. We can understand the value of fulfilling projected needs by extrapolating over the useful life of a new system. And we can define quantitative operational objectives and the concept of operation. So the general product of these activities are the list of operational objectives and the system capabilities. In terms of functional analysis or functional definition, we translate the operational objectives into functions that must be performed. And we allocate functions to subsystem by defining functional interactions and organizing them into modular configuration. So the general product of this activity is a list of initial functional requirements, which we have discussed in class. And then we have the feasibility definition or physical definition. And here we visualize the physical nature of subsystem conceived to perform the need system functions. And then we can define a feasible concept in terms of capability and estimated cost. So again, this is at the macro level, but varying the trading off the implementation approach as necessary. The general product of this activity is a list of initial physical requirements. And then step 4, we get the needs validation, which include designing or adapting an effectiveness model. This could be analytical, like math-based, or simulation, computer-based, with operational scenarios, including cost, market, factors, etc. We define the validation criteria. So this is the performance that the system must accomplish, and demonstrate the cost effectiveness of the postulated system concept after suitable adjustment and iteration. Then formulate the case for investing in the development of a new system to meet the projected need. The general product of these activities are a list of operational validation criteria. And given a successful outcome of the needs analysis process, it is necessary to translate the operational objectives into a formal and quantitative set of operational requirements. So this is the needs analysis phase flows diagram. So again, these are the 4 steps on the right-hand side of the systems engineering method. And we have the external inputs coming through the left side. And then we have the input outputs that are necessary, and the functions that are necessary for each one of the steps. So for instance, at the operations analysis, step 1, we get the predecessor system as an external input, and we use that to analyze the projected needs. So let's say we have here in Ingram School of Engineering, we have a building that can be occupied by 10,000 students. Maybe we need a bigger building of 20,000 students. So we can do 2 things. We can build a new space, or we can change the layout of some of the floors of this building, or maybe add a new level to the building, and so on. So those are we try to forecast the projected needs, and then we can also define an operational approach of what are the options. And then moving forward into the functional analysis, what are the things that we need for this new space? What are the things that we need to accomplish in this new space? Maybe we are trying to bring a petroleum engineering to Ingram School of Engineering. So how do we translate the functions that are needed for this building to be able to accommodate such a need? And we can allocate those functions to subsystems. So maybe we need access to some new materials into the building. So how do we kind of bring this into the building? Maybe we need some new subsystems for our system, which is the building. And then moving into the feasibility definition, do we have the technology that can allow us to bring these new liquids or these new materials into the building? Do we have let's say, maybe we need some air conditioning, some special type of temperature for some of these materials, or maybe they need to be stored in special place or location. So do we have the technology? And if that's the case, if we don't have it, is there any technology that we can use and purchase or bring to the building? And if there's multiple options, then we can define some concepts, maybe multiple concepts, and then we move forward. We can design a model, an analytical model that can allow us to forecast the cost and the performance, and making sure that, I mean, with the output of those models, that the needs are validated in terms of budget, in terms of performance, and so on. And that would be at the top level. How can we handle this needs analysis phase using the systems engineering method? So let's talk about operations analysis. The first issue that must be addressed is the existence of a valid potential market for a new system. The development of a new system or major upgrade is likely to be very costly and will usually extend over several years. So accordingly, a decision to initiate such a development requires careful and deliberate study. So how do we analyze these projected needs? We need to first understand the deficiencies of the state of the art, maybe the benchmark or the system that you're using right now. So in virtually all cases, the need addressed by a projected new system is already being fulfilled, at least in part, by an existing system. So one of the first steps in this needs analysis process is the detailed identification of the perceived deficiencies in the current system. So again, for your project, I want you to identify, because there are some agencies, volunteers that are already trying to help with the problem that is defined for your project. So you need to understand what are at least the perceived deficiencies of what's happening right now. The above process is most effective when it combines accumulated test data with analysis, often using existing system simulation. This approach provides two major benefits: a consistent and accurate evaluation of system operational performance, and a documented history of results, which can be used to support the formal process of need analysis if new development programs become necessary. Another thing could be obsolescence. This is the most prevalent single driving force for new systems. And this can happen in from multiple number of reasons. For example, the operating environment may change. The system may become too expensive to maintain. So for example, we are transitioning to new computers. Let's say, in October 2025, computers that we have here in the Ingram School of Engineering are becoming obsolete. So we're gonna need to buy some new computers that can use some of the latest technology and operational systems. The parts necessary to repair may no longer be available. That happens a lot with the current cars. I mean, if you own a vehicle, it could be as new as 2017. You might not be able to find parts for such a vehicle now after COVID, because some companies decided to shut down some of those manufacturing facilities, or it become very, very difficult to find. Competition may offer a much superior product. Technology may have advanced to the point where substantial improvements are available for the same and lower cost. So vigilant self-evaluation should be a standard procedure during an operational life of the system. Operational objectives. The principal outcome of the operational studies is the definition of the objectives in operational terms that our new system must meet in order to justify its development. So again, two different cases. In a needs-driven development, these objectives must overcome such changes in an environment or deficiencies in the current system as have generated the pressure for an improved system. In a technology-driven development, the objectives must embody a concept of operations that can be related to an important need. Although objectives should be quantifiable and objective, the reality is that most are qualitative and subjective at the early stage. So these are some of the rules of thumb that can be helpful. The objectives should address the end state of the operational environment or scenario. It focuses on what the system will accomplish in the large sense. Objectives should address the purpose of the system and what constitutes the satisfaction of the need. Taken together, objectives answer the why question: why is the system needed? And most objectives starts with the infinite word provide, but this is not mandatory. In terms of objective analysis, the term objective analysis is the process of developing and refining a set of objectives for a system. Typically, the product of this effort is an objective tree, where a single or a small set of top-level objectives are decomposed into a set of primary and secondary objectives. The composition is appropriate until an objective becomes verifiable or you begin to define functions of the system. When that occurs, stop at the objective. So here's an example of an objective tree structure. Most objective trees span 1 or 2 levels deep, and there's no need to identify extensive depth. So here you see the overarching objectives, and then second, two to three primary objectives, and then 3 to 5 secondary objectives, and then the functions. So an example of objective analysis, think about a new car. Suppose an auto company wants to design a new passenger vehicle, which it can market as green or environmental friendly. Understanding the objectives of this new car establishes priorities for the eventual design. So the company management begins an objective exercise, forces the company to evaluate and decide what's important when developing a new system. Therefore, it is worth investing some time, energy, and capital in determining what the overall objectives of the system are. So in the car company, the company might soon realize that the overall objectives of this new vehicle is to provide users with clean transportation. So that will be the top level objectives, does not include performance, cargo capacity, of road capability, and so on. In the overall objectives are 2 keywords, clean and transportation. Both imply various aspects or attributes of this new car. Since both words are not yet well defined, we need to decompose them further. But the overall goal is clear. This vehicle is going to be environmentally clean and will provide sufficient transportation. So here's an example of the objective 3 for an automobile. At the top, we have provide clean transportation, and then we have some 4 objectives, which includes provide a comfortable ride for 4 passengers, achieve at least 35 miles per gallon, meet all federal safety standards, and achieve a base retail price of $15,000. And then in terms of providing a comfortable ride for 4 passengers, there's 3 additional objectives here. In determining whether an objective needs further decomposition, one should ask the following questions. Does the objective stand on its own in terms of clarity of understanding? Is the objective verifiable? Will the composition lead to better understanding? And are requirements and functions really implied by the objective? So in our example, we can argue that the 3 of the primary objectives are sufficient as stated, and all 3 are verifiable. Only the subjective objective leading to comfort needs further decomposition. In this case, comfort can be divided into 3 components: a sound system, a noise level that allows conversation, and physical space. Awarded in the figure, these 3 could all be verified by various methods. And having objective 3 focuses the development effort on the priorities. So functional analysis. At this initial phase of the system development process, functional analysis is an extension of operational studies. And they're directed to establishing whether there is a feasible technical approach to a system that could meet the operational objectives. At this stage, the term feasible is synonymous with possible and implies making a case that there is a good likelihood that such a system could be developed within the existing state of the art without having to prove it beyond reasonable doubt. So translation of operational objective into system functions. First, you visualize the type of system that could carry out certain actions in response to its environment that will meet the projected operational objectives. This requires an analysis of the types of functional capabilities that the system will have to possess in order to perform the desired operational actions. The visualization of a feasible system concept is inherently an abstract process that relies on reasoning on the basis of analogy. This means that all the elements of the concept should be functionally related to elements of real systems. So next we have feasibility definition. The feasibility of a system concept and therefore of meeting the projected need cannot be established solely on the basis of its functional design. The issue of feasibility must also address the physical implementation. In particular, system cost is always a dominant consideration, especially as it may compare to that of other alternatives. And this cannot be judged at the functional level. Accordingly, even at the initial phase of the system development, it is necessary to visualize the physical makeup of the system as it intended to be produced. It is also necessary to visualize all external constraints and interactions, including compatibility with other systems. What is necessary to consider the physical implementation of the projected system in the needs analysis phase. This does not imply that any design decisions are made at this time. In particular, no attempt should be made to seek optimal designs. Those issues are dealt with much later in the development process. The focus at this point is to establish feasibility to meet a given set of operational objectives. It is the validation of these objectives that is the primary purpose of the needs analysis phase. So we want to start visualizing the subsystem implementation for our future system. So given the allocation of functions to subsystem, it is necessary to envision how these might be implemented. At this stage, it is only necessary to find a sample of similar functional units in existing systems so that the feasibility of applying the same type of technology to the new system may be assessed. We can also look at the relation to the current system, where there exists a system that has been meeting the same general need for which the new system is intended. There are usually a number of subsystems that may be candidates for incorporation in modified form in the new system. Whether or not they will be utilized as such, they are very useful in building case for system feasibility. So even though the system that we are proposing might not be completely or close to that design, existing design, we can still use some of the information from that system to validate what we want to do. Other less tangible factors can also come into play, such as the existence of a support infrastructure. So what that means is if you have already the infrastructure around for the operation of that system. So I brought the example in class of Tesla, that when people started traveling over the Thanksgiving break, the infrastructure was not there. Still, I mean, if you go online, you'll see many, many examples. And when these cars start running out of battery, they don't have a place to charge. And then they have to basically rely on gas generators to plug in these vehicles in order to be recharged. So the final goal of having or rely on fossil fuels is basically not there anymore. So that's all related with the infrastructure. So in terms of, in the case of a car engine, many years of successful operation has been established a very wide base of support for conventional reciprocating engines in terms of repair sites, part suppliers, and public familiarity. Because of the prospective cost for changing this base, innovative changes such as the Wankel rotary engine and design based on the Stirling cycle has been resisted. The point here is that beneficial technology innovations are often overridden by economic or psychological resistance to change. So again, great ideas, but if they're not economically favored or even psychologically, for the customer, then they might not prosper. In technology-driven system, it's more difficult to establish feasibility by reference to existing applications. Instead, it may be necessary to build the case on the basis of theoretical and experimental data available for such research and development work, as has been done on the candidate technology. In case this proved to be insufficient, limiting prototyping may be required to demonstrate the basic feasibility of the application. Consultation with outside experts may be helpful in adding credibility to the feasibility investigation. In terms of cost, the assessment cost is always an important concern in the needs analysis. This task is particularly complicated when there is a mix of old, new, and modified subsystems, components, and parts. Here again, cost models and maintenance records of the current system combined with inflation factors can be helpful. And your economic analysis class is also helpful in this case. By comparing similar components and development activities, cost estimation will at least have a credible base from which to work. In the case of new technology, cost estimates should contain provisions for substantial development and testing prior to commitment for its use. So in terms of definition of a feasible concept, to satisfy the objectives of the needs analysis phase, the above considerations should culminate in the definition and description of a plausible system concept and a well-documented substantiation of its technical feasibility and affordability. The system description should include a discussion of the development process, anticipated risk, general development strategy, design approach, evaluation methods, production issues, and concept of operations. In terms of needs validation, the final and most critical steps in the application of the needs systems engineering method is the systematic examination of the validity of the results of the previous steps. In the case of the needs analysis phase, the validation steps consist of determining the basic soundness of the case that has been made regarding the existence of a need for a new system and for the feasibility of meeting this need, an affordable cost, and an acceptable risk. In the concept development stage, the analyses that are designed to estimate the degree to which the system concept may be expected to meet the postulated set of operational requirements is called operational effectiveness analysis. It is based on a mathematical model of the operational environment and of the candidate system concept being analyzed. In the effectiveness analysis, the operational environment is modeled in terms of a set of scenarios, postulated actions that represent a range of possible encounters to which the system must react. So scenarios, basically, if you're looking at the environment, for instance, if you have a system that has to be operating outside, you have to put a scenario in which you consider cold weather, hot weather, wet conditions, winter conditions, and so on. So that's what we refer to as scenarios in terms of operational environment. And then you want to see the performance, and if that performance is close to what you expect. Usually, initial scenarios are selected to present the more likely situations, followed by more advanced cases for testing the limits of the operational requirements. Validation of a feasibility and need. Finally, the effectiveness analysis described is mainly directed to determine whether or not a system concept derived in the functional and physical definition process is feasible and satisfy the operational objectives required to meet a projected need. Finally, the last topic for today's lecture is the system operational requirements. The primary product of needs analysis is a set of operational objectives, which are then translated into a set of operational requirements. The system operational requirements that result from the needs analysis phase will establish the reference against which the subsequent development of a system meet the projected needs will be judged. Operational scenarios, again, logical method of development operational requirement is to postulate a range of scenarios that together are representative of the full gamut of expected operational situations. While scenarios range widely in their content depending on their application, we are able to define 5 basic components of almost all scenarios. First, the mission objectives. So these scenarios should identify the overall objectives of the mission presented and the purpose and role of the system in focus in accomplishing those activities. In some cases, this component is system independent, meaning that the role of any one system is not presented, only a general description of the mission at stake and the objectives. So in a commercial example, the mission could be to capture market share. In a government example, the mission might be to provide a set of services to constituents. In a military example, the mission might be to take control of a particular physical installation. So in our project for the class, we are looking at the mission similar to the government example, which we are trying to provide services to these people in need. The architecture scenario should identify the basic architecture involved. This includes a list of systems, organizations, and basic structural information. If governance information is available, this will be included. This component should also include basic information on system interfaces or a description of the information technology infrastructure. In essence, a description of the resources available is provided. So in a commercial scenario, the resources of the organization are described. In a government scenario, the organization and agencies involved in the mission are described. In a military scenario, these resources could include the units involved with their equipment. Physical environment, the scenario should identify the environment in which the scenario takes place. This will include the physical environment as well as the business environment. Neutral entities are described in this section. For example, customers and their attributes will be defined, or neutral nations and their resources. Competition, the scenario should identify competition to your efforts. It might be elements that are directly opposed to your mission success, such as software hacker or other type of enemy. This might be your competition in the market or outside forces that influence your customers. It could also include natural disasters such as tsunami or a hurricane. And then the general sequence of events. The scenario should describe a general sequence of events within the mission context. The scenario should allow for freedom of action on the parts of the players. Scenarios typically provide a general sequence of events and leave the details to analysts using the scenario. At times, the scenario may provide a detailed sequence of events leading to a point in time, whereby the analysis starts and actions may be altered from that time forward. Scenario could include much more depending on its application and intended purpose. They come in all sizes, from a short graphic description of a few pictures to 100 pages of text and data. The only means for judging whether or not requirements are complete is to be sure that all situations are considered, and this is very important. So we need to take into account every possible situation. For example, the range of temperature or humidity of the storage site may drastically affect the system life. And that's the final slide. So we're going to stop here and we'll continue our discussion in our next lecture.